All right. Thank you, Dr. Papo. Dr. Panan, can I share my screen instead of you? Can I
Yes, if you would like to, you want to present from your own computers, right?
Yes.
Yes, sure, definitely. You can do it, yes.
Oh, but I don't think I have the option to do that. Wait.
I'm not really sure. Are you familiar with Zoom?
I think it's fine. Yeah, but just I did need to update something there, but it's okay. Maybe just go ahead with this presentation.
Okay.
All right. Thank you, Dr. Papo and Dr. Panan. All right. So, good morning, ladies and gentlemen. My name is On Jin Xian or On Jin Sean. I'm a lecturer at the School of Engineering, Monash University, Malaysia. So Monash University Malaysia campus is about a 30 minutes drive from Kuala Lumpur city center. So if you come to visit Malaysia, please, you're welcome to visit me or our campus as well. And the title of my keynote presentation today is Investigation of Heat Transfer Enhancement in an Annular Conduit using Functionalized GMP Colloidal Suspension. All right. Move to the next slide. So today I will start my presentation with introduction, followed by my research work. And then my research work is separated into two parts. I will talk about radial fins in part 1. And for part 2, I will talk about swirl-inducing fins. And then followed by future works, research implications and contributions, and acknowledgement. A heat exchanger is a device that helps transfer heat between two mediums. So our objective here is to improve the efficiency of the heat exchanger. So there are different types of heat exchanger. For example, heat and tube heat exchanger, double pipe heat exchanger, and plate heat exchanger. So different conduit were used in different type of heat exchanger. A number of conduit design and modification have been employed to achieve better heat transfer by researchers. So we have wavy tube, annular tube, various duct shape like square, triangular, pentagonal, etc. And we have a vortex generator or inducer like fin, lured strips, and etc. This is a wavy tube. It is useful in generating a recirculation zone near the conduit wall. So as you can see here there is a little bit of recirculation zone here. But the drawback is the recirculation zone may be too localized. That will cause uneven heating. So this is the annular tube. This is a very simple type of heat exchanger, and it is essentially used in double pipe heat exchanger, suitable for compact heat exchanger, and have been improved by some researchers with addition of vortex generators or fin inducer. Then we have various duct shapes. As you can see here, we have square and circular. However, the research survey revealed that poor heat transfer was observed when conduit with edges were employed. For example, triangular, rectangular, pentagonal. So the circular pipe heat exchanger or the conduit proved to be a better type of heat exchanger. And pressure drop was negligible between different shapes as flow rate increased. This is the vortex generator or inducer. We have a lured fin in the figure 4, porous fin in figure 5, and helical fins in figure 6. So this design modification is to improve heat transfer, include using longitudinal fins, porous fins, and helical fins. So in order to improve heat exchanger efficiency, we can modify the geometry, like what I explained just now, or we can use different type of working fluids, or we call it a thermal fluids. So in our research, colloidal suspension we use to enhance heat transfer capacity. Nanoparticle we use, but it can categorize into two categories, metallic and non-metallic. For metallic, we have aluminum oxide, copper oxide, platinum oxide. For non-metallic, we have carbides, carbon materials, and etc. The addition of nanoparticle enhances the thermophysical properties of the base fluids. Colloidal suspension. So the creation of this colloidal suspension involve either one-step method or two-step method. Okay, what is a one-step method? The one-step method is the colloidal suspension created by having the solid substance dissociate into nanoparticles within the base fluids. And then we add additive such as STBS, or we call it a surfactants, to prevent agglomeration. For two-step method, the colloidal suspension is created by mixing nanoparticle of solid substance that is prepared separately into a base fluid. The base fluid can be water, ethylene glycol, or oil. And then we use ultrasonification to maintain stability of the suspension. This method is more economic, viable, and it can be mass produced. Okay, this is the research work. As I told you just now, there's two parts of my research here. The first part, we analyze the effect of using a radial fin using the GNP-based colloidal suspension. And for second part of my research, we use angle fins to induce swirl, also using GNP-based colloidal suspension. And both research use CFD simulation to produce result for a given geometry. We use ANSYS software to run the simulation. And the grid convergence study was performed to estimate the ideal grid density. So for part one of the research, it's titled Investigation on Heat Transfer and Pressure Drop Performance of Different Concentration of GMP-based colloidal suspension flow in an annular passage with inner fin configurations. So if you see the protrusion here, it's actually the fin, right? So when fluid pass through this area here, it will create a recirculation zone here in the purple color area. And this red or orange area here will have increase in the flow rate or the velocity. So here we will have a heat transfer enhancement in this area. This is dimension of the geometry. So we use the flow rate from 4 liter per minute to 10 liter per minute, which with 2 liter per minute increment in each step. We use constant heat flux and concentration for 0.025, 0.05, and 0.1 weight%. So this is the result for part one of the research. As you can see here, this is the fin result with a dashed line and the smooth pipe. That means there's no fin. So fin and smooth, the result shows the fin and smooth annular geometry with different concentration, better heat transfer performance with colloidal suspension was observed. So as you can see here, the temperature, we have managed to achieve a lower temperature here with the fin type annular geometry. And however, the heat transfer performance was not significantly increased in concentration when we add in more nanoparticle. So it increased, but when we add in more, the increment is not that significant anymore. All right, so same goes to the heat transfer coefficient and the Nusselt number. All right. So again, this is the result for the thin and smooth annular geometry with different flow rates. Okay, you see 4 to 10 liters per minute. And we know that heat transfer increases when we increase the flow rate. Right, so you can see that the highest heat transfer can be achieved using the highest flow rate, which is 10 liters per minute. And it is the best heat transfer is achieved at 10 liters per minute with thin and annular geometry. So with thin is better than the non-thin. So this is same goes to heat transfer coefficient and the Nusselt number. So the improvement of heat transfer is significant, but the increase in pressure drop is not significant. So the pressure drop was determined to have 65 Pascal. So this is very little, and increase when the radial fins of the given specification was introduced at 10 liters per minute. But the heat transfer improvements were up to 27% at 10 liters per minute. So the heat transfer improvement was significantly more compared to the pressure drop. Right. So we don't want the pressure drop to be too much in our case study here. This is the second part of my research. So it is titled Investigating Heat Transfer Performance Using GNP-based Colloidal Suspension via Functionalized closed butt extract within annular geometries with swirl-inducing fins. So as you can see here, we introduce an angle fin here so that the flow becomes swirl when it passes through the fin. Right? So we increase the fin from 10-degree angle to 40-degree angle. This is the geometry of the second research. So it is tested with flow rate from 2 to 12 liters per minute with 2 liters per minute increment in each step. And constant heat flux was applied to the outer wall. And GNP was used with concentration of 0.025, 0.075, and 0.1 weight%. Okay, we have three Reynolds number here, which is 1,000, 3,000, and 6,000. As you can observe, when the angle increase from 0, which is a non-fin, to 40 degree, the temperature drops, and this shows that the highest heat transfer is achieved at the highest degree, which is a 40 degree. And this is applicable for most of the cases, but here for 3,000, a bit strange here. But in general, all the heat transfer performance better when we increase the angle of the fin. Okay, this is the result comparing between the distance of the angle fins. So, which means that we have more fin or less fin in our annular geometry. So as you can observe, the distance change from 100 millimeter to 200 millimeter in spacing, or the distance between the fin angle. The result shows that the smaller distance, the better for the heat transfer performance. So as you can see here, when we decrease the distance from 200 to 100, which is the blue color one, so we have a better heat transfer performance for all the angle. All right. So, and then this is applicable for Reynolds number of 1,000, 3,000, and 6,000 as well. So the pressure drop was determined to have up to 35 Pascal over the 0.9 meter length. And when the angle fins of 40 degree was used at 12 liters per minute, and the heat transfer was improved up to 8% at 12 liters per minute. So again, here it is shown that the heat transfer improvement is significantly better than the pressure drop. So in the future works, we will try to determine what is the optimal design for the heat transfer improvement, but we want to have minimal pressure drop. All right. And we also want to determine what type of colloidal suspension and concentration to be used for the different type of heat exchanger. And the preparation method for the colloidal suspension itself should be focused on the environmental friendly one. So we don't want the preparation method to pollute the environment. And it must be scalable, means it can be mass produced, and economic as well. Okay. Research implications and contributions. So the result from our research here can be used or to be informed to the heat exchanger user or manufacturer, or what's the geometry design should be used, and colloidal suspension type and concentration, as well as its effects on a given geometry, can be known also. So this can be shared with the manufacturer and the user as well. Acknowledgement. So I would like to thank Professor Kanda. She is the Director of Research Institute of Rangsit University, Program Chair of RSU 2021 Conference. And I would like to thank also RSU 2021 Conference Organizing Committee, especially Dr. Papol, and Dr. Panan. And also I would thank Monash University Malaysia for the support provided to attend this conference. Okay, thank you very much. And if you have any question, please feel free.
Thank you, Dr. Un.
Thank you.
Anyone has questions, please feel free. Anyone, please? If not, then I will have a quick few questions.
Okay.
GNP, is that stand for gold nanoparticles?
No, sorry. GNP stands for graphene nanoplatelets.
Oh, graphene.
Yeah.
And why it has to be graphene? Because it has a good heat transfer.
Yes, you got the heat transfer, and actually not many studies has been carried out yet on this heat transfer, especially on this different type of geometry. So we want to know what is the effect of using this GNP in this geometry. And also GNP can be produced in the environmental friendly way. So this is very good, and we don't want to the process of producing this colloidal suspension to be to pollute our environment. So that is very crucial.
Yes. May I ask a little bit? Is this graphene is the thinnest material on Earth? That's the one that's on the research. That's this crash from the pencil. Is that the same thing?
Yes. Yeah, it was. Let me check again. I think one slide says that the graphene was found in 2004, I guess, by a researcher from University of Manchester.
Yes, in UK.
It is one of the thinnest material. So it only have one layers of atoms.
One of the atoms. Yes. Yeah. Oh, wow.
So
everybody can hear this.
I'm not sure whether it is the thinnest material on Earth, but it is one of the thinnest, right? Yeah.
Yes. Okay. And you said that you simulate in ANSYS. So what kind of numerical algorithm do you use? Do you use a mesh-based algorithms like finite volume, or you use a meshless, like smooth particle hydrodynamics?
We use finite volume, yes.
Finite volume,
with mesh, yes.
Okay, with mesh. Okay, I see. And can you give us a short conclusions that so whether we have high turbulence or low turbulence is better for a heat transfer?
Sorry, blend?
Should normally, if we have a high turbulence, that will promote the better heat transfer, right?
Yes.
Am I correct?
Yes, you're correct. Yeah, yes. But we don't want to create too much turbulence, because the turbulence also create pressure loss. So if you need you need to loss of power to drive the fluid flow. So we don't want that as well. So we have to balance between these two. We want a high heat transfer, but minimum pressure drop.
So that is the optimum point, that balance between the
Yes. Yes. So,
the rate of turbulence, the level of turbulence, and also the
yes.
flow can still go smoothly.
Yeah, that's why we need to do a lot of simulation and experiment to determine the optimal type of fin we use. We don't want it to block the flow, and then we need to use a lot of power to pump the fluids. So that
I
is
see.
yeah.
Ah,
So
okay.
this is the balance between these two things.
Okay, thank you. That's very good point. Thank you so much.
Okay, great. Thank
So
you.
anyone has questions? If not, so please give a big hand to Dr. Un.
Yeah, thank you.
And thank you so much.